All right, so basically we're going to do some math with phase changes and with what's called specific heats of metals, which then lead to phase changes. But we have to have the backup information before we can do this. So this goes with the liquid and solid stuff. It's a different way to look at it. And honestly, if you are in engineering or chemistry in college, depending upon like what track you're going from that, there are entire courses over. This stuff is really called thermochemistry and thermodynamics. Like I took a whole semester physics course on thermodynamics. So we're just barely touching the surface, but you need to at least see what it is. Some of this works into physics really nicely, and it also works really nicely with our chemistry stuff. So when I take or talk about energy, we talked about it one way in physics. Do you remember what that little short definition for energy was? Yes. Ability to do work. I hear Grace over there, or I see Grace. So that's how we talked about it in physics, and we even had a formula for it. If you remember, we had energy can be equal to work, and work was equal to a force times a distance. So that's just old news. What we add to it when we're talking about thermochemistry is the ability to do work or transfer heat. We didn't look at the heat part of it too much in physics. We said, oh, that's non-mechanical energy, it's heat energy, it's lost to overcome friction, whatever. When we talk about it in chemistry, we have to think about the heat energy as well, because that's your heat of reaction. That's what makes something endothermic or exothermic. So this is where your endo and exo comes in. I think we probably should also get just a little blip on, whoops, thermodynamics, like how is it actually defined, and thermochemistry. So for thermodynamics, we'll just keep it simple. We'll say the study of energy and its transformations. So when I talk about thermodynamics, I'm just talking like on the surface, I'm talking about Ke and Pe, and those two things combine and how they change to equal the mechanical energy of the whole system. When I talk about thermochemistry, I'm actually talking about the study of chemical reactions. And energy change that involves heat. Okay, any questions about those things? So I think we probably should also remember mechanical energy versus non-mechanical. Here's where we have Ke and Pe. The KE is the same. It's the energy of motion. Doesn't matter if I'm talking about particles or if I'm talking about a kid pulling a wagon. It's still this 1/2 mv squared that we used in physics. When I talk about potential energy, I could be talking about potential energy gravitational, which was mass times gravity times height. Or I could be talking about chemical potential energy, which has to do with bond energies. This non-mechanical stuff, that was like heat energy, I don't know, wind energy, solar, nuclear, light, really I should say electromagnetic, then it covers all of it, electromagnetic radiation. So when I'm talking about a chemical reaction, I have mechanical energy plus non-mechanical energy. I have KE and I have PE. Plus, I'm just going to make a H for heat for now. Okay, so I want you to see if you can write this down. The law if I were to ask you to write that right now, see if you can do it. Give me the law of conservation of energy. Did we all at least write something down? Yeah, turn around to the person next to you and check yours with theirs. See if they look the same. You might have to move. You might have to actually walk. What'd you write down, Connor? Oh, okay. Okay. That's pretty concise. What'd you write down, Kaylee?
I said energy cannot be created or destroyed, it just changes form.
Boom. Mara, what'd you write down? Okay, so here's what happens a lot of times. Energy cannot be created or destroyed. That's not the whole law of conservation of energy. The most correct way to say the law of conservation of energy is energy cannot be created or destroyed, only transformed. Which is pretty much what Kaylee said and pretty much what Connor said, and I think it's pretty much what you said. I didn't hear the end of yours, Mara. So we got it. Now, what you really didn't know is actually what you're stating there is the first law of thermodynamics. That word is too long. Energy can't be created or destroyed, only transformed, or it only changes form, is the other way you'll see it. This is directly related to phase changes and also specific heat. Now, because we're going to be working with this in lab, there are some terms we have to know, so we know what we're talking about. So the first two things when we work with this stuff in lab that we have to think about are the system and the surroundings. So you have to define your system when you do these things. And if you read this in any kind of chemistry book or physics book, it talks about this. This always seems weird to me, but it talks about it as a portion of the universe. Like it always says, I don't know, maybe not always, but most books I've ever read talks about this in terms of the entire universe. So when I talk about the system, I would say that it is a portion of the universe. Let's say, I'm trying to make this short, singled out for study. Like we're going to do some labs with the calorimeter where we just use water, but we do different things with the water. So your system might be just the water, or it might be hydrogen and oxygen. Whatever is contained within that calorimeter, that little thing you just put in your bin, would be considered your system. The surroundings are everything else. All the stuff you're not concerned with in your experiment. Now, I think I gave you a picture. Yeah. If you look at this picture, which I gave you, and I wanted you to have these because they're pretty good. This whole thing really is a cylinder. Like what you would see, you might find one of these in an engine, actually. The whole premise on how the piston, the cylinder, those things in an engine work. So if I look at this thing and I look inside, I can see that the matter that I have in there, it can't leave the system. My system's closed off. I have a way that energy can enter or leave the system as heat or as work done by this piston, by compression and expansion. So I can define my system, which is my hydrogen and my oxygen, and then everything else that's part of this picture would be called the surroundings, including the stuff I didn't show on the outside. So in this particular thing, I'm only worried about what's happening to my hydrogen gas and my oxygen gas. Ooh, and if I compress it enough, what will it do? Do you know? What? It does condense. If I put enough pressure in there, it will condense and liquefy, and I will have water. Now, where else do we have this principle of a piston and a cylinder Well, I already told you in an engine, but what are we working with in an engine? The combustion engine. You've heard of that before, right? Where would you find one of those? In your car. Have you ever worked on an engine? Anyone in here? Yeah, all right. That's part of the premise of how your car works, the combustion of gasoline, right? You have a combustion engine in your car. Does it have pistons? It does have pistons. And it has, isn't that amazing? Chemistry on the way to school this morning, people. It's all around you. You cannot escape it. All right. All right, so we have to define our system types. All right, we have 3 different types of systems. The first one is the most difficult to work with. It's called an open system. In an open system, I'm going to call it the region being studied. Whoops. So whatever I'm studying, whatever I've defined as my system, can exchange both heat and mass with the surroundings. This is the most common kind. This is the kind of system we have in everyday life. Like if you're getting together Friday night, if it's not snowing, maybe you can have a bonfire. A bonfire is a great example, although I think it's supposed to be like 80, so we probably won't want a bonfire by then. But anyhow, a bonfire is a great example of an open system. Both mass and heat are exchanged with the surroundings, yes? I don't have as much mass left of wood as what I started with after a bonfire. A lot of that has been given off to the surroundings. Obviously, heat is given off to the surroundings during that chemical reaction. So that's type 1. Type 2 is called a closed system. If I have a closed system, whatever region I'm studying, can only exchange heat. Not mass. Goes back to the closed system for a reaction in chemistry. Remember, conservation of the law of matter. Matter can't be created or destroyed. It only changes form, just like the law of conservation of energy. So when I have a closed system, that would be like your calorimeter that you're going to use in lab. So there will be an exchange of heat going on, normally between 2 substances, maybe between one substance and the actual calorimeter itself because of what it's made of. There's some heat transfer. So it depends on the lab which part you'll be studying. And then the third kind is called an isolated system. So we have two extremes, we work in the middle. So it doesn't exchange anything with its surroundings. No heat, no mass, nothing. And then I think, is your second picture, does it look like this? Did I give you this one? Yeah? So it's the same picture, it's just saying now, if I have a truly closed system, I'm not going to lose any mass. It's exactly the same picture. All right, makes sense so far? So when we're looking at our system, whatever we define as our system, we're going to be looking at internal energy. This internal energy is equal to the sum of all KE and PE. I'm going to say of all, since we're in chemistry, we'll say of all compounds or components of the system. Internal energy is just represented by a big E. Normally, I would say when we start, so we don't usually like define it, give it a number when we start, but what we usually look at is how does it change? Is work being done? Is heat being given off? Those are the things we focus on when we look at this stuff. In the end, we want to say, do we have a loss? Or do we have a gain of E? Now I want you to take the next diagram. It should look like this if I did it right. And I want you to really carefully read through that. Like, take your time and make sure it makes sense to you, because you're going to have to use these probably on a quiz. So really read through it and ask questions if you need to. I think it's fairly straightforward. So when I look at this, like for me, this is one of those things that like, hey, this actually makes sense. Because when I'm losing energy, my arrow's going down. So that like in your brain to me, like that sort of clicks better than a lot of these things do. And also if you read this, when energy is lost to its surroundings, then my E is negative. And in my head, I don't know, that just makes sense to me. If I lose something, I'm negative. Unlike an ion, when it loses an electron, it becomes positive. You know, that's one of the hardest things for Chem 1 people to get, because you're losing something and yet it's positive. So this seems to make sense because I'm losing and I'm negative. Opposite over here, ooh, the arrow goes up. Yep, I'm adding some energy. And when I add energy, then my delta E is positive. Okay? So let's look at that in a little formula. So I can say the change in internal energy which I signify as delta E. Remember, delta means change in, is the final energy of the system minus the initial energy of the system. Or I can write it like this, which I much prefer. Delta E is equal to E sub final, or E sub F minus E initial, or E sub I. There are graphs that go with this too. I don't know if I gave you this one. Check and see. Which again, I think this is, I sort of hesitate to call this a graph, chart, I don't know, diagram. Easy to read. Initial state, final state. Oh look, there's a red arrow and it's going down. I could ask you some questions like, which is greater, initial or final energy? Well, we went down, so the initial energy of the system is obviously greater than the final. So I could say that energy, I hate to say lost, energy was transformed, perhaps I could say, and in the end, I'm going to get a negative number. It's going to be less than 0. Does that make sense? All right, so then let's look at this. If delta E is greater than 0, if delta E is greater than 0, what must be true about final energy compared to initial energy? If my change in energy is greater than 0, what has to be true about final versus initial energy? What, Mara? Yeah, so in this case, I would have my EF is greater than my EI. And I would say the system absorbed energy from the surroundings. So I'm going to write this. EF is less than EI. And then I want you to write a statement that tells me about that equation, or that equation. If EF is less than EI, what happened to the system? Grace, what'd you write down? If EF is less than EI.
The system gave off energy to the surroundings. She's not in, so we're just making sure.
Oh, okay, she's here.
Okay, thanks.
She missed one. Do you want to watch? Okay, Grace, I'm sorry. Read it again.
The system gave off energy to the
Good. So the system gave off energy. We just have a little bit more, you guys. Okay. All right. So I have just a tiny bit more I want to cover today, and then I'll give you time to work on your problems. What you're going to be working with in lab, let's see if I have another marker that works. They're actually called thermodynamic quantities. And any thermodynamic quantity will have three parts. They're going to have some type of a unit, which normally, we're talking about energy, so it's either kilojoules or joules. They're going to have, obviously, a number value. And they're going to have a sign. So they're either going to be negative or positive. If I have a positive delta E, a positive change in internal energy is how I would say that. This would be when the system gains energy from the surroundings. If I have a negative delta E, then the system loses energy. To the surroundings, and that you can think of, like, I think when we talked about it before, we said gave off. So obviously when we look at all of these things, energy is being exchanged. We have to figure out how or why. So when I have an energy exchange, we'll say between system and surroundings, There's two things that could be happening. Two ways it could be exchanged. So there's two ways it can be exchanged. We've talked about both of them already. Can you name them? What's one way that energy is exchanged, the more obvious way? Anybody want to talk to me? Y'all want to look at your paper? Nobody even wants to look at me. What do you think, Braven? You got any idea? How has this energy been exchanged in everything we've talked about? Look back a little bit. Look back. I think we just said something about it. Oh, it's okay. What's the form of energy? That might be a way to say it. What kind of, yeah, okay. So, there's one, woo! Okay, heat. Now the other one you have to think a little farther back too. We learned it in physics. I talked about it at the very beginning. A force over a distance. Work. So work can be done on, whew, it's painful today. Work can be done on the system. This heat is Q. Work hasn't changed, it's W.
Why is it Q?
Because normally it says quantity of heat. And heat is used in a lot of different formulas, and there are other formulas where it's used as a capital H. So, anytime we work with specific heat, phase change, thermochem, or thermodynamics, heat is Q. So I can say that my change in energy, internal energy, is also equal to Q plus W. But we must pay attention to sign. That means we have to think, is this a positive or a negative situation? So I'm going to spell that out for you so you'll know as you move into this what you should be looking for, or how you should figure it out, I guess. So really, we've had two formulas for delta E. All right. So this will help you interpret the problems, like when you're given something in words to figure out what's going on. So let's talk about Q first. If it is positive, the system gains heat. If it's negative, the system loses heat. For W, if it's positive, I say work is done on the system. And if it's negative, work is done by the system. that would be like the example of the piston in the engine. And then for E, positive means a gain of energy. By the system. Whoops. And negative means a loss of energy. By the system. So when you read them, you have to really, think about what's going on in terms of sign. And then the only two other things we really have to think about when we look at this, I would say, is when heat is absorbed, from the surroundings, then I have an endothermic process. And then the last thing would be this. All right. I think that's a lovely place to stop today. So tomorrow we have to take some more and then we'll work, I'm gonna give you some specific heat stuff, like what we'll do in lab, and we'll practice some problems with that before we actually go into lab. This morning, nope, I did this before I left yesterday. Page 204, 21 through 27, and then 29, 30. And you have almost a period to get that done, so work away. I'll just travel around and answer questions, okay? Chloe, we missed you today.